Okay, so very good morning to all the participants and our distinguished expert. Thank you, sir, for joining with us, and accepting our invitation for giving to give a expert talk. Now I will call Ankita to introduce her to the participants. Then we'll start with the session.
Good morning, everyone, to the last day's first session of our FDP. And today with us is Dr. Harpreet Singh, sir, who is currently working as a professor at IIT Ropar. After doing B and ME in mechanical engineering, he did his PhD from IIT Roorkee in 2005. During his PhD work, he worked on high temperature corrosion of superalloys and its prevention by plasma spray coatings. He has been doing extensive research work in several areas related to surface engineering and manufacturing since the year 2002. Has authored 10 book chapters and contributed more than 195 research papers in various international and national journals. He has done pioneering work to explore the use of cold spraying to develop erosion corrosion resistant coatings. He has completed and has been pursuing several national and international sponsored projects with funding from MHRD, DST, CSIR, DRDO, EPSRC, IUSSTF, GCRF, and UKIERI. He has been doing several consultancy projects with industry in surface engineering and additive manufacturing. He has 4 Indian and 3 US patents to his credit, along with 7 patents under processing. He has produced 22 PhDs, whereas 11 more are currently working under his supervision. He has visited several countries, including USA, UK, Netherlands, Australia, Canada, South Korea, Spain, and Germany to attend various international conferences and as part of academic delegation. He has also coordinated several short term courses and delivered many expert lectures in various institutes in India and abroad. He is a recipient of Kansai Nerolac Excellence Award for the Excellence in Coating Research, Young Scientist Award, Career Award for Young Teachers, and Maharashtra State National Award for Research Work done by the Teachers of Engineering Colleges 2007 by Society for Surface Protective Coatings India, Punjab Academy of Sciences, AICTE, and ISTE, respectively. The government of Punjab awarded him with Achievers Award for the year 2019 for his several contributions as an educationist. A recent breakthrough by his group is the development of novel and economical technology for surface coatings, named as grind coating process, which is now successfully patented in US. The proposed sustainable technology can be used to deposit a metal coating on metal surfaces, ceramic or glass. He has also established a national facility on cold spray at IIT Ropar, which is one of its kind and has the capabilities of additive manufacturing in addition to surface engineering. He is an adjunct professor at Swinburne University of Technology, Australia also. Sir, we are very privileged to have you here with us, and I would request you to please start your lecture. Thank you, sir.
Thank you very much for the introduction. So, first of all, let me share my screen. And um, okay, I think I'm already sharing my screen. Can you see my presentation here?
Yes,
Hello.
yes, sir.
Is it visible? And
Yes,
I'm audible.
sir. The screen is visible and you are audible clearly, sir. Thank you, sir.
Okay, thank you. So, first of all, thank you very much for the organizers to give me this opportunity to interact with the participants here. I can see a diverse range of participants from several parts of the country. Today, my agenda is to talk about cold spray based additive manufacturing. Now, what I'm going to, tell today is that how the cold spray can be used as an additive manufacturing technology. Of course, as a participant of this course, you must have gone through all the traditional ways of doing additive manufacturing, which includes several laser-based processes, then binder jet, and EBM, and so on. This is another, set of I would say, non-conventional additive manufacturing process where cold spray is being used for additive manufacturing. So, cold spray per se is basically developed as a surface engineering technology where the main focus is basically to develop coatings. But then people started exploring its capabilities to deposit very thick deposits of the order of few and later on then they started exploring standalone parts to be manufactured by cold spray. Now why we say it additive manufacturing process? Because by definition additive manufacturing is process where we are adding the material in layer by layer fashion. Same thing can be done by cold spray because cold spray can disperse or dispense the material layer by layer, right? The only challenge, somebody may say that why not all the surface coating techniques are used for additive manufacturing? Because most of those surface engineering techniques, they will fail to deposit thick deposits beyond certain range, right? Especially some of them are limited only to few micron thickness. But cold spray has been, able to give us success or liberty to have very thick deposits. That is and why it is depositing thick deposits. We will understand as we progress through this lecture. Okay. So what I am going to talk about today is, of course, I will give you plenty of information about cold spray process because whenever you want to do some research or understand any area, that technology must be understood. Only then you can explore its potential to its full. So we will talk about some of its fundamental aspects, and then we will talk about some applications uh, in coding area as well as in the additive domain. In a way, I will tell you how cold spray evolved during these years, because cold spray is not very old process, I would say, especially when we compared with the other coating technologies. So, let me start. No, this is the first slide, which is about my group. My group has several students as in the introduction. Almost 2023 students have already passed their PhD from this group. Our lab, what we call your lab, and several more are doing their research work. So what I'm here is basically due to my research scholars, my students, who have been helping me to understand this to greater depth, because I completed my PhD in 2005, and after that my role is more like manager, to manage funding and kind of mentor the students. But the actual work is done by these PhD students, master students, and so on. So I owe all this credit to them, my students. Now, we started working in surface engineering basically ever since I joined my PhD in IIT Roorkee in 2005 itself. So we started with the thermal spraying technology. In surface engineering there are several kind of different technologies, um, right from physical vapor deposition, chemical vapor deposition. Then we have several others, even electroplating and so on. There may be more than 15 categories among that. But our focus was more on thermal spraying, which we will understand very soon. So this, so in a way, my focus for the last several years is mainly on thermal spray and exploring its various generations. As you can see this, when we talk about surface engineering, then comes the question that what kind of applications we are exploring. My research is more like applied in nature, which can be directly applied by the industry. So we explored several areas or several application areas in the surface engineering, right from power plant boilers, because they have this problem of high temperature oxidation, erosion, etc. So we developed several kind of coatings by different technologies um, within the thermal spray space. So we did work on plasma spray, HPF spray, detonation gun spray, cold spray, and so on. Then we developed coatings for hydroturbines also through high velocity flame spraying and HVF spraying. And of course, biomedical coatings, we developed some coatings, and there we have worked on high velocity flame spraying, cold spraying. These are few applications. In fact, now we are working in certain new areas also, such as defense coatings and so on. So things are evolving day by day as we are, getting older in this thermal spraying research. Now, another aspect which we have started very recently, I will say, additive manufacturing. Now, again, here our emphasis is not on the selective laser or selective laser sintering or melting or those kind of processes. Rather, as I told you earlier, we are trying to explore cold spray capabilities for additive manufacturing. Why? Because we'll understand why it is an attractive option to us. So that we will understand as we progress through this. This is a little bit about what kind of research we are doing in this your lab, what we call. Now, since I use this word thermal spray now, what is thermal spray basically? So thermal spray is basically a process to develop the coatings, right? So we want to develop some coatings on some substrates through, what will be the feedstock? Feedstock could be, powder, or it could be wire also. Now the idea here is that we melt the powder. Typically, we used to melt the powder or the wire, and then we will propel it with certain velocity towards the substrate. Substrate is a substance where we want to, develop the coating. So suppose I want to develop coating on this surface. So I will heat the materials or sometimes melt the materials. So then those materials will be, pushed with high velocity towards the substrate where they will stick on the surface. Now, this is basically TV process. Thermal spray coating process is basically TV process. So means temperature and velocity process. So we heat the materials, we propel them, means we give them some velocity, and then we ask, allow them to solidify very quickly on the surface, which we call sublat. So typically, you can imagine the material is being heated and then propelled, so it will come in the form of some splats, we call it, right? So these are basically lumps of materials, molten materials, which will come and sit on the surface. So you will get a typically layer by layer structure here in this. So you will keep on tracking the gun, these torches or thermal spray guns is the name which we usually use. So this spray device here, what we you can see here, this is basically called gun also in certain references. Certain times we call it torch and so on. So this will be tracked over the surface, right? Time and again. So you will keep on layering by layers of that. So what we call typically laminar microstructure you will get, right? So this kind of structure we make um, in this thermal spray process. Now, how the material gets stuck on the surface, there are different types of theories. We will not go into detail for thermal spray, but of course, we will talk about only one technique, that is cold spray. Now, cold spray is also among this family, right? So, if you see the evolution of thermal spray technologies over the time, so this is almost more than 100 years ago, the concept of thermal spraying came actually. If this is a nice diagram by Davis. Now here you can see Scoop. Dr. Scoop was the first who conceptualized and patented this idea of thermal spray in 1910. Actually. Now, quite often I want to emphasize here is the power of observation. So Scoop saw his child playing with the racket and the ball, and he was playing with against the wall, right? He was pushing the ball with the racket towards the wall, and that is coming. Now from there he got an idea what would happen if I have metals, molten metal, and push them towards the say wall or the substrate, and what whether they will stick or not. So from there he got this idea, and he started his work, and he developed these some of these initial variants of thermal spray, which was more like electric energy based, and then later on flame also came into picture. So see, when I say temperature, so temperature, how it will come? It can come from some fuel, or maybe from electric energy and so on. So that is where people started using this these options. So wherever we were using flame, we call it flame spraying based processes. Wherever we are using this electric arc, so these are basically based on electric energy. So we use the word arc and so on. But as you see, the things kept on changing with the time. The race was to, first race was to develop high temperature materials. I would say the materials having high melting points like ceramic and so on. There people started thinking about, plasma spray, because we need very high temperatures. So of course plasma is very high temperature, plume. So people created plasma through certain gases and then introduced the powder to propel them towards the substrate to get deposits. So that was plasma type, right? But then slowly people started having some technologies for low temperature, melting temperature materials. So then comes HVF and so on. One thing is very clear that people try to, in general, what will be our approach? Approach is that we try to reduce the role of temperature in thermal spraying or in any process for that matter, because temperature we use only if it's absolutely necessary, actually. Because temperature comes with, of course, some kind of eco concerns, but at the same time with some money, and it also degrades the properties of the materials, both the materials. coating powders as well as the substrates. So one evolution which took place in this area is that people started to decrease the temperature in these processes, and to compensate this TB thing, they started increasing the speed or the velocity of the particles. And in that thing comes this cold spray, right? So if you see the cold spray, the role of temperature has been minimized, whereas the this velocity has been increased tremendously. So that is one aspect of it. Another thing which I would again like to emphasize here is that the this power of observation, as I told you. This paparin actually, how this cold spray came into idea into picture was that once this paparin's group was doing some experiments in the wind tunnel. So in wind tunnel, they were pushing some materials, this fluid flow over some building model, and there they could see some metals particles which are entrapped in the this flow. They are getting stuck on the surface, and from there, then these they got idea about why not to do it only with the help of velocities, because in that wind tunnel the velocity was very high. So from there on, he started exploring it, and they could very easily develop some of the very, soft materials. At least they start with aluminum and so on, and then the whole evolution started in somewhere late 1980s, and then things kept on changing. Then, of course, then came this warm spray and cold spray, the CGT technologies in Germany. They took a lot of initiative. With I know some of those people. Dr. Karthi was also one of the instrumental in developing these cold spray equipment, initial cold spray systems. So from there, the things started emerging, right? So what you can see that in cold spray, the role of temperature, if you see here the picture, this thermal spray processes, we on one side we have this flames temperature, on other side we have particle velocity, right? So flame could be generated by arc or anything, right? Or by some fuels. This flame is used in that fashion only, although in arc. So now here you see the different generations of thermal spray. If you see here, we have this particle velocity on this side, and cold spray lies here. You can see this cold spray. The temperature, working temperature, are typically less than 1000 degrees Kelvin even, right? And you can see HVFD guns, this high energy plasma spray comes here, which has a very high temperatures, right? But the velocities are less. So flame spray lies here, where temperature is significantly higher, but the velocity is very low. So what we are essentially getting here, because as I told you, the temperature we are not appreciating much in any process, because this leads to some kind of phase transformations or material oxidation, right? Because powders, usually the most frequently used feedstock is powder in thermal spray, and and the powders are very active, so they get degraded when the temperatures are high. But and that is something which we want to avoid. So that's why we started thinking of lowering the temperature, process temperatures, right? And what are the advantages we are getting while we are increasing the particle velocity? We are getting reduced porosity. We are getting very good interlaminar cohesion between the particles. And this cohesion is basically responsible or the energy or driving force behind the cold spray to be chosen as a tool for additive manufacturing, because if the interlaminar cohesion is good, that means you can develop very thick coatings, right? because yeah, if you see in plasma or other processes or flame spray for that matter, so what will happen after a typical thickness, you will not be able to retain further material on those coatings, right? And you become restricted in terms of the thickness to be achieved. Basically, it is due to interlaminar cohesion differential. So, thermal spray in itself is a good market. I would say it is now fairly popular market. By you can see here plasma and all these generations of thermal spray are getting good amount of market, and of course cold spray is picking up. Here it is 10% global market. These are some figures which show that yes, there is a demand for thermal spray technologies. And of course, still right now, plasma spray is still it is enjoying a very good market share. But then the cold spray is also having its own niche market. So it is coming up into this transportation and so on. Transportation anyway is the biggest lever for our cold spray. When I say cold, transportation, I mean at aerospace and automobile sectors. So there, this cold spray is getting much recognition by because mainly its solid state nature means that the rolled off temperature is very low and the quality of the deposits is very high. So cold spray market definitely is picking up. And if you see now in any thermal spray conference, you will see a lot of emphasis research is being done on cold spray these days because people see its advantages in two domains. One is surface engineering, and another is additive manufacturing. So that is making it. Now this brings us to cold spray process. Let us try to understand the cold spray process. So as I told you, we are majorly dependent upon the velocity, right? So here the velocities are very high, typically supersonic velocities, right? So means Mach number is more than one. Okay, so we are reaching to Mach number 2, 3, and so on. Now, then how to do it actually? So getting a supersonic jet is not an easy job. So that is being done with the help of these supersonic nozzles. Okay, so which are typically those who are good in thermodynamics, they would know that usually we have these supersonic nozzles which have converging and diverging sections, right? So we have throat here and we have this converging and diverging section. Now, the role of this nozzle is basically to achieve a supersonic jet of a gas, a typically gas. So we are using nitrogen, or initial variants they were using air itself and then helium. So the three options are frequently used, but this air is used for low pressure cold spray systems. Um, but for high, I mean, when I say low pressure means 10 bar less pressure systems. But if we have high pressure systems, we have to go with nitrogen. And if you want to have very high purity coating, then helium is a good choice. But then everything comes with some price, and we have to have kind of selection manual to make such decisions. Now, coming back here, so we are achieving a supersonic jet of gas, one thing. Another thing which we are doing is we are introducing the powder particles into that supersonic jet. Now, what would happen? We can well imagine that there will be momentum transfer from the gas to the particles. And those particles will also achieve very high velocities and they will go and stuck on the surface, right? So this gun is then transversed or in a raster scan fashion or some other fashion on the surface, and we will get the deposition. So here we have some logistics here. We have this electric heater also. So from here the gas would come, right? And we have this powder feeder also, and we have this electric heater also. Now the powder feeder is where you will introduce your powder, right? And then it will be pushed into the nozzle. Then this electric heater is basically used to heat the gas mainly. Now this temperatures could be up to 1000 degrees Celsius also of the gas. Okay, now somebody may say that the how it is cold. Now why? Because this temperature is mainly for heating the gas, because this will assist us in getting higher velocities, right, for the same gas. Because otherwise, if the gas is cold, it can become still colder when it is expanded at the throat of this nozzle, right? We know that there will be sudden expansion, and then the temperature can go very low, and that the velocity of the gas will reduce, which is not beneficial here, right? So that is the major reason. But additional feature we come, or advantage we get, is the particles will also get somehow, they will pick up the heat, and they will also become softened. But this temperature is never so that it will never so high that it would create any kind of metallurgical loss to our particles, right? So in a way, it is a solid state process. Then there are certain, further fundamental insights into it. Now, here, you know, every time this velocity, when you say velocity, it's not that you will propel the particles and they will stick on the surface at any velocity. So what that means, we have some critical velocity in the particle, only then we will get the deposition. Otherwise, deposition will not happen. This is a nice diagram which is shown here. You can see here we have some material deposition on this axis, which is represented in terms of deposition efficiency. So deposition efficiency is what? Basically, it means that if 1 kg of powder is thrown towards the substrate, how much is, what percentage is retaining as a coating, because there will be some loss of the material, right? So that is basically deposition efficiency. So as an engineer, we will always have to have its high value, right? Because we don't want to waste our powder, which are costly most of the time. So, so material deposition is happening on this y-axis. On x-axis, we have what you call velocity. Now, this velocity and deposition efficiency has a strong correlation here. So you can see that at certain velocities, you will have no deposition at all. Means, so this kind of scenario will be that particles will rebound. Actually, the particles will rebound. Okay. So, but there will be some critical velocity V critical here. After that, the deposition will start. Say like this. You can see this is a particle. This is the substrate here. So some kind of bond will start becoming here. And then we keep on increasing the velocity, then there will be a good bond here, as you can see. And the deposition is really very high deposition rate. Although here deposition is happening, material deposition, but at certain range, you will get very good deposition in this form. In fact, this is the ideal thing. I'll come on that. And you will get very nice deformation of the particle as well as the substrate to get very nice adhesion between these two. And once we reach this point, so we have this. But then going beyond this velocity will also not be beneficial. Rather, there will be a chances of erosion of the substrate. Like this, you can see these nice pictures here. So beyond that, there's no use in increasing the velocity. So you will get this loss of deposition. So as an engineer, we can always define a window of deposition, and the point to be remembered here is that this window of deposition changes as you change the combination of materials. When I say combination of materials means the substrate and the particle. Two materials are there. One is feedstock material, another is substrate. So as soon as this combination is changed, this process deposition will change. In fact, this is something which we have to do whenever we want to cold space certain materials. So some effort goes into that also to bring the parameters at this level or to achieve this critical velocity and window of deposition, right? Now, another thing to be remembered here is that, okay, before that, so what is happening here? So what you can see here, typically we are getting deformation of the particles. So deformation, which material will deform? It will be ductile material, right? Brittle material will not deform at all. You can see here, brittle materials, we are not getting any deposition, right? So this is one of the challenge which is still there in cold spray process. It's difficult, in almost very difficult, almost impossible to deposit brittle materials. Although there is some kind of research which is happening, people have shown some minor depositions, but anyway, maybe at this 2009, this figure is taken from that reference. At that point, there was no brittle material deposition. So you can see literal material. Why? Because there's no deformation. Yeah, you can see here, this process is basically deformation based. This is a nice simulation done by my student, Vinay, who has shown us the single particle impact on the substrate here. You can very well see that the particle is coming and then striking with the enormous kinetic energy. You know, the velocity is very high, so I'm half mv square. It will come and then it will strike on the surface. There will be deposition, right? So we are getting the deposition owing due to this deformation, plastic deformation, which is happening. Now, depending on the nature of this in the simulation, both the substrate as well as this both are deformable, right? So both are deforming. This is an ideal condition. Uh, so cold spray will be very good option if both the materials are ductile, right? Um, Now, another thing which is happening here is to be noted is that the temperature at the interface is increasing, especially. You can see this. So temperature at the interface of this particle and the substrate is increasing. And this is something which is good for us to have this kind of what you call jetting phenomenon. So what happens when this localized temperature increases? This is very localized to the interface of the particle and the substrate, right? And what would it do? And let me tell you this, everything, all these things are happening in a very minor amount of time actually, okay? They are much less than 1 second. So because the standout distance typically is very low, 40 mm or so in cold spray. So everything is happening, but that's why we call it severe plastic deformation process, right? Extreme and rapid plastic deformation process is this. Now, what is happening in this is that at the interface, the temperature is so high that there is a localized melting, according to one of the theories, which is widely accepted. So this localized melting is what is making this bond even more stronger, right? Of course, deformation is helping us, but this localized thing. Now, since the temperature becomes very high, so reaching to the melting temperature, so what would happen? You will expect that the shear stress of the of this material will fall off to zero. And when it goes to zero, so there will be very easy kind of flow at the interface, and you will get something, you know, this kind of jetting outside. You can see this kind of jetting outside. That this jetting, what they call, brings both the materials as a lock-in kind of locked kind of feature here. See this beak type of thing of just like some word. So what it is having? It is having some material from the coating powder as well as from the substrate, and this kind of thing is ideal for us. And people say this severe kind of this going down of this shear stress to zero. This phenomenon basically they call it adiabatic shear instabilities, ASI phenomenon. And most of the people agree with this theory. But there is another theory which is hydrodynamic plasticity theory, which says that this is not necessary. Uh, that we have this interface adiabatic shear instability. Rather, it is just hydrodynamic plasticity in both the materials which is making the things. But now most of the simulations, of course, one of the challenges in cold spray is to see these things experimentally. Very very difficult because everything happens in microseconds and so on. But most of the simulations are now showing that this adiabatic shear instability is more kind of probable kind of mechanism, and that's why ASI is now given more recognition over hydrodynamic plasticity theory, right? Well, so now I think this makes sense, and you might have now got some idea about how the cold spray process works and what are kind of mechanisms in this technology. Now, as in the introduction, people said that we have set up this facility at IIT Rockford also, cold spray facility. We have this system from plasma Kicken, and this is very high pressure, I would say. This can go up to 50 bar pressure and 1000 degrees Celsius temperature, right? So since this system is creating a supersonic, this is a partly we can see this gun actually. I'm sorry, I don't have the full figure of the system, but anyway. So this is the gun, what we call cold spray system. Here we have this nozzle outlet. Now particles will be introduced from here, right? And gas and everything will come from outside. Now everything is done in an acoustic chamber. Why? We can well imagine that we have this supersonic jet of gas which will create a lot of noise. So we have this acoustic chamber and so on. So here we fix the part, the sample on which we want to develop the coating, right? And let me show you this video. You will see material coming out from this nozzle, right? Uh, the the point here is that in cold spray you don't even see this jet actually, right? Because there's nothing burning or there's no flame, per se. But if you see HBF or plasma, you will see just like in oxyacetylene gas, you see the flame, no? That kind of flame you see. But in cold spray, you see nothing actually. Only deposition you will see on this target material. So let us see if it works. So it's a very small video. This shows the actual operation. How so this gun is carried by a stroke. So you can ask the thing on the gun, and we are getting the thing on. You can see the thing is coming, I mean, steam coming out of it. So you see the deposition is right on the. Okay, so now then from scientific point of view, this particle impact basically will depend upon uh, particle velocity and particle temperature, right? Now, then particle velocity, how it is controlled in cold spray, that will depend upon the stagnation. Temperature means the temperature, pressure, the pressure at which you are giving the gas to the nozzle. Process temperature also, because as I told you, lighter the gas, more will be the particle velocity. I mean, I will say more will the temperature, more will be the velocity of the gas, and hence the particle velocity, right? And the nozzle dimensions, type of carrier gas, right? Helium, nitrogen, helium among these three, you can get very high velocities through helium. Nitrogen is kind of a trade-off between air and helium. The problem with helium is, although you will get very high quality coatings, but it's very costly, right? So sometimes economics will not work in that, and of course there is other parameters, particle size, density of material, morphology of the. Similarly, particle temperature will depend upon the type of carrier gas, process temperature, nozzle material, and so on. So there is a lot of scope for playing with some of these parameters in the search, if not experimentally, but in simulation studies, right? Let me tell you, there's a lot of research being done in simulation of this process also. As I said, practically it's very difficult to monitor this process and its dynamics, right? So we have certain system parameters and we have some feedstock material also. So these are two things. So basically, while doing this coating, we will be mainly controlling the pressure, right, and the temperature in the system, right? And pressure will then dictate this. Other important process parameters with which you can play the scan speed, right, and stand-off distance, spray angle also will, dictate the properties of this one. So these are all process parameters which one should look into while developing. Now the question is, why cold spray is being used or becoming popular for surface engineering as well as additive manufacturing. So one is that no melting of water takes place here, right? So that means the chances of oxide formation, etc., they will be reduced, especially when we have this low melting temperature materials like aluminum, etc. So this gives us an added advantage, right? And plastically deforming the feedstock powder will improve the mechanical properties. It has been seen that since you are doing the severe plastic deformation of the particles, their grain size also improves. Improves in the sense that it becomes refined and you get very good mechanical properties in the deposits, which is another very attractive point. Coating thickness, yes, as I told you that we have very good adhesion or cohesive strength between the layers. So you can use it for additive manufacturing as well, and as well repair. Repair is also kind of a domain in manufacturing itself, um, uh, done just like as we do the additive manufacturing, right? So repair means typically here again we need to have some kind of thick deposits or deposits of high quality and so on. I'll show you some examples. Recycling of powders is important or possible, at least in this case, because powders you are not damaging their chemistry. So we get, as I said, getting 100% deposition efficiency is not possible. So some part of powder will definitely go here and there, right? That can be recollected and recycled. There is another processes it is not possible because it gets melted and so on. So these are some of the attributes. Another attribute is that high deposition efficiency. If you compare it with other processes, of course, high deposition rate. Now this is very attractive feature here. High deposition rate means you can deposit, for example, with our system, if everything is optimized, you can achieve in say 10 to 12 kg per kg per hour deposition, which is very good actually. In your conventional heater manufacturing processes, this cannot be achieved so fastly, right? So we can deposit at a very high deposition rates, and that is something which is kind of making cold spray process uh, attractive for a heater manufacturing. Working with dissimilar metals possible. Thermally sensitive materials can also be done, and dense as well as porous coatings can be obtained. I'll show you the beauty that not only very dense, but you can have porous coatings or porous structures can also be made. Then what are the limitations? Limitations are basically two. Coatings are brittle due to extensive plastic deformation, right? So they become very brittle. So that means you have to sometimes do some kind of post treatment to remove that brittleness, right? And economically, it is challenging, of course, because of the higher volume usage of the process gas. Actually, okay. So, for example, nitrogen will be used in ABAS in our system, right? So that becomes challenging. Of course, people are trying to kind of recycle this gas also. Uh, Probably in the future we'll get some good kind of economics in this aspect also. But this brittleness thing, of course, in certain applications, it's fine to have brittle, no problem. But in certain other cases, you have to have some kind of heat treatment to reduce this brittleness in the deposits. Here's another very interesting kind of observation that oxide content in the generated CS coatings is less than the oxide content of the feed powder in the terms of ppm. What does it mean? Whenever you get some feedback of feedstock powder, it will have some kind of oxide content, right? In terms of having, because these powders are very active, so you will get some kind of oxide layer on the powder particles. Now, what it has been seen in the cold spray deposits, that oxide content has even reduced, which is interesting, right? Instead of having oxidation of powders, we are getting reduced. So this observation is basically coming from the fact that when the particles are going, suppose there is a particle which is having some oxide layer. So oxide layer is usually very brittle. So as soon as it strikes on the surface, that oxide layer disrupts. It goes away, flakes away, and you get adhesion. So that is something interesting which has been seen in some of the studies. So then comes sorry, evolution of coating feedstock in the cold spray. This we also should understand because this gives us an idea that what kind of range of materials we can process by cold spraying. So people started, as I told you, they started with the very soft metals and alloys like aluminum, copper, zinc, etc. Then feasibility of these refractory materials was also done, and successfully these materials have been deposits. So you see these are pure materials, pure metals, right? And then of course some alloys were also done. And then we have hard metals and alloys. Slowly people expanded to this also, like titanium alloys, inconel alloys. These are very difficult, right? He and VMGs. Then people started doing composite coatings, ceramic, and so on. See, up to 85% of ceramic coatings have been produced, right? Which is amazing actually. So this is also done. Now, current trend is metallization of polymers, metal polymer composite coatings. The people are exploring whether polymer coatings can be deposited on on certain other substrates, or vice versa, that you have a metal and can be deposited on the polymer and so on. So this all kind of research is happening, and this also gives us the what kind of flexibility in terms of materials we have with may desire such problem and so on. Then what kind of feedstock morphologies have been used? People have used metal and alloys, which are atomized powders, right, or crust powders, right, the standalone powders. Then we have these kind of hard phase and encapsulate, and uh, encapsulated by some outer binder, right? So these materials have been also been deposited, right? So we have a ceramic or composite-like coatings, right? And one way of doing these kind of composite coatings is that you have a soft binder and you have a hard particles. You just blend them and then deposit them. You will get this kind of morphology. But here you have more control over this phase. Then there is another approach where we have soft phase and hard phase. These are kind of sintered, and then we are uh, depositing them, and we get this matrix of both these phases. Sorry, the final microstructure of having both these phases as compared. So,
Good morning, sir. Sir, one question, please.
yeah.
Sir, in ceramic coating, what are the substrates you are using?
Substrates are diverse actually. We can use even steels, right?
Okay.
And of course, pure matter is not a challenge, right? Steels, even superalloys also have been used. Do you
Uh,
have something special in your mind? We can talk about that.
Actually, sir, my research work is for it's a pressing pellet formation, about 1 inch pellet by metal oxides, high temperature metal oxides. Not exactly coating; it's a ceramic pellets formation by cold spraying.
See, again, ceramic is a very kind of brittle. So
Okay.
pure ceramic pellets you can't make actually by cold spray.
Okay.
But if you add some reinforcement, like just here metal ceramic up to 85% it is showing.
Okay.
So if you have some say ceramic, say silicon carbide or something of that sort, you have to add some metal binder into it.
Yes, yes.
Maybe.
But we're
Hmm.
using
Hmm.
organic binders. We're using only
Hmm.
it's hot cold pressing. That's it. The powders are cold
Yeah,
pressed and sintered. That's it.
yeah, yeah. Well, that is the best approach which you are using. Maybe may not be you need this cold spray actually because that will not the economical option, for
Okay.
your application. So pallets by this pressing, uh, what you call powder metallurgy route, है ना? This is
Mhm.
fine, not a
Yeah.
problem.
Mhm.
If you want to deposit it as a coating, then it makes sense actually. Hmm?
Sir, in these ceramic pellets, can we deposit like zinc powders in pure form?
Say again, zinc
Uh,
powder.
Sir, I made the pellet by ceramic powders. Sir,
Hmm.
in this, as a electrode, can I use the pure zinc powders?
Yeah, zinc powder. You means both you will blend and then you will deposit,
Yes,
right?
yes, huh.
Hmm?
In the form
Yeah,
of
that
powder.
is possible. Yeah, that is possible to make some coupons out of zinc plus this ceramic,
Yeah,
and then you can deposit them as some coins or some what you
yes, yes.
call.
Is it possible, sir?
Yeah, it should be possible.
Okay, thank you so much.
What thickness you are looking for?
Sir, only few not more than that.
Yeah, it's possible, but again, economics. I don't know. Economical तो नहीं
So,
होगा ये.
so not required
Unless
for economic, but only for that analysis, that laboratory experiments.
Yeah,
That can.
that can be done. Yeah.
Oh, okay, sir.
Yeah.
Thank you. So no oxidation will be there while doing for
Oxidation
this.
will not be. Oxidation will not be there. That is very sure.
Okay.
Um, and
Actually, sir,
even for
actually,
economics,
sir,
what we
mine.
can.
Actually,
Mhm.
sir, I want for electroding that zinc as the anode in the powder form, and in the other side as cathode as silver powder. So
Mhm.
both side I have to coat. Usually, I am doing by the sheet metals.
Mhm.
But if this cold spraying is good, then it can benefit to my product.
Yeah, yeah. I mean, it should be given try actually.
Okay.
Right? Yeah, you see, I'll give you number of my students, contact ID, or you
Okay.
write an email to me. I
Thank
can
you so much. Thank you
then
so
we
much.
can discuss this problem with my group, and then probably we can come to
Sure,
some.
sir. Okay, sir. I'll be in touch with you. Okay, sir.
Uh,
Thank you.
no, yeah, in fact, for making coupons, for economics to work, we can deposit over large area, and then we can cut the coupons also.
Okay.
So, those kind of approaches can be thought of.
Okay, sir.
Hmm. Well, as I told you that if there are some challenges, in terms of getting the desired properties, people have done some interesting work in terms of post processing of these deposits also. For one approach would be that we go with heat treatment, right? So heat treatment, we all know that it can mitigate the porosity, it can improve the intersplat bonding, just like in your sintering. This, for example, this is a as coated uh, substrate, right? So this is the coating. So we have in the coating, you will see very clearly the splat boundaries. But once you heat treat, these splat boundaries can be merged and you can get better intersplat bonding, right? So this approach is being used, but there is some other interesting work people have done. Some people are doing this stress relaxation by post deposition short pinning also, right? Then laser assisted cold spray is also being tried, right, to get the desired ductility in the materials. In situ hammering is another interesting application where people are, using these slightly bigger hard particles, which are just giving the hammering effect, and they're not getting deposited. Rather, they'll come, they'll hammer. It's like in situ pinning kind of thing, right? So this hammering, what it will do, it will increase this adhesion between the layers, right? Cohesion is improved by this, but then they'll rebound and they'll go back, right? So this is laser remelting is another approach, mainly to tailor the properties of upper layers only. When you do the heat treatment, the whole layer will get affected, right? But laser gives us the liberty to have effect only for the upper layers only. For example, if you have a corrosion problem, you can mitigate the porosity in only upper layers, right? By controlled exposure of the laser and so. So then another question which is very practical actually. As I told you, whenever you have uh, a new combination of materials means the feedstock material and the substrate. Now, still there is a lot of discussion that what kind of surface roughness of the substrate should be there, because surface roughness will definitely affect it, right? The properties or the adhesion, and it's quite challenging in several combinations. Our practice shows that the deposition of first layer is very very challenging, right? So there, see in thermal spray, other processes where mechanical keying is the main mechanism of bonding, वहाँ पे there is no contradiction. People say, okay, bring some kind of hard, surface roughness on the surface. It will help us to pin the particles on the surface. But in cold spray, this is not working. So we have seen that there are certain combinations where the surface roughness is helping, and there are some combinations where the surface roughness is not helping actually at all. For example, this is a very good study done by my student Surinder Singh on surface roughness effect. Now, here we were having this combination of SS316L steel, and there is a copper, right? So this is some application, a very new application which we explored uh, for our this nuclear reactors actually. So they wanted to develop very thick coatings of 3 mm on the stainless steel. This is very challenging because they wanted pure copper coatings without any oxidation. And this work is being done in several countries because they want to have very nice oxide-free coatings of copper. Not for this corrosion or other things, but they want to have this passivation of currents, plasma currents, and so on. For this, they need very high thermal as well as electrical conductivity. So there, when we started our experiments, the adhesion was not coming on certain rougher surfaces. But then we have this mirror polished surfaces also, where the adhesion was very good actually. So what was the reason? We understood it by single particle impact experiments. There we could see that um, roughness in this case was not happening because these peaks on the surface, when the surface is rough, it will have hills and valleys, right? So those peaks or they were getting deformed. This is the deformed copper particle. This is the deformed peak. Now this deformed peak energy is not much that it will plug this. So there were some gaps we saw in the SCM images. But when the surface was perfectly mirror polished here, this much roughness. So we could get a very nice adhesion here. You can see copper and substrate, they are adhered very well. So here, this worked very nicely, and we could get very good adhesion strength when the roughness was mirror polished level. But you will see the literature, there are certain other combinations where you will see that the surface roughness is helping. No, our understanding mainly comes from the fact that if the substrate material is very hard or having enough strength that these peaks are not getting deformed, then probably surface roughness can help. Why? Because if, for example, imagine if this would have not deformed, it would have been staying in its straight position, and the particle would have deformed over it, and good adhesion would have been achieved. So probably where we have a hard surface and a slightly ductile material, coating material, probably their surface is helping. But in these kind of mirror polish will help us. The lesson from here is that still we don't have any recipe for unknown material. If you come to me with some unknown material that sir deposit this combination, we have to have some kind of experimentation based on surface reference also, because we don't have the reference uh, sure recipe for this surface reference. Now then comes some of the applications. So we have seen the fundamental things, most of them, but then the capabilities. See, I'm showing you some of the case studies here, again done at here. So this is a nickel chromium based coating. Now here we have added 26, 24, 25% titanium carbide in these coatings. You can see these are composite coatings basically, which we developed very nicely, and we could see that they were giving us very good erosion corrosion resistance actually. Very good in fact. So, and these additions were helping us to get better and better properties. So this is the coating thickness. This is some experiment done in the actual boiler, experiments. So you can see uncoated was showing a lot of thickness loss, but this thickness loss was reduced after our compositions. These are all developed by cold spray, and you can see the structure of these coatings. Nicely adhered coatings, nicely distribution of several elements in that this one, and oxygen was weak around. Then this is another set of nanostructure coatings which we again developed at IIT Ropal itself. So again we could develop very nice coatings with the nanostructures, right? And erosion corrosion was further decreased. This is a conventional coating which was again discussed, developed by Neerjwala, and but then Manoj did some nanostructure things, and then he could further improve the erosion corrosion resistance, right? So this is the effect of we are showing the effect of heat treatment, as I was showing you that these deposits can be heat treated and you can get better adherence and better electrical conductivity. As I told you, this is the same study where we these copper coatings on stainless steel, and our objective was to achieve this electrical conductivity of this level, and we could achieve it after heat treatment. So heat treatment, especially this is quite understandable that both will improve. Thermal conductivity as well as electrical conductivity can be improved after heat treatment, because that will merge some of the boundaries and you can get better conduction and so on. So this is about metallization of polymers, right? So you can see some polymer coatings have been deposits. Okay, and these are all glass fiber composite, PC, ABC, ABS, and even we also do this copper coating on the PMMA substrate, right? That IIT Ropal. This pure copper coating could be deposited on this PMMA sheet and so on. Okay, copper coating on different polymer substrates have been produced, right? So these are all having nice applications in several domains. Bond codes for TVCs. This is something of the interest to aerospace industry. Because those who are aware about this thermal barrier coatings, so usually thermal barrier coating are provided on the blades, turbine blades, but the problem with them that the TVCs are mostly ceramic, and then we have the substrate which is some alloy and so on, and there is a lot of CT mismatch. What is that CT? It's a coefficient of thermal expansion mismatch. So that is compensated with the help of these bond codes. But the bond codes, they produce their own challenges in terms of their oxidation and so on. So there is a lot of research going on in that domain, and people are trying to develop better and better bond codes. And again, some studies have shown that bond coat by cold spray can be very interesting. These are further applications of other coatings. So these are titanium coatings, cold sprayed on coatings, so dense coatings, having very nice properties. Biomedical application, again, again very promising area in terms of even commercialization also. A lot of research is needed in this direction. And the biomedical coating is one where we are looking for certain porosity. Actually, it's the other way, right? If we talk about most of the applications, we are not wanting to have porosity. But in biomedical applications, we are interested to have some porosity. Rather, if it can be interconnected, it will be very good, because then it will help us to have cell growth and whatever they call it, uh, to be very intact, right? And surface roughness also we want to achieve. So those things have been successfully achieved by uh, these cold spray, right? So we can tailor the parameters, or we can play with the parameters of cold spray process in such a way that we can have desired porosity in the coatings, right? You can see such a nice porosity, in biomedical application, you may be needing porosity more than even 30% and so on. So there are some interesting kind of studies done by people. Of course, we have not done it at IIT Rockwood, but these are case studies from the literature. So you can see these nice coating structures. These are biomedical coatings we developed at IIT Rockwood. Here the purpose was to bring some kind of wear resistance and corrosion resistance, and we developed these composite coatings where we introduced this ceramic baghdite. Baghdite is basically a new material which is seen as a replacement to HAP, which is traditionally used. Now HAP, although it's an excellent material, but it has a lesser mechanical strength. So when we are talking about some sliding contacts, right, or wherever in the implants, wherever there is a chances of wear, so there this Baghdad is having better properties because it has some zirconium. Of course, it's again calcium derivative, but it has some kind of zirconium which gives us a better kind of hardness or mechanical properties and so on. So we did this. Avnish Kumar has done this research very recently. He's completed PhD. So then there are some other, so many materials have been tried by cold spray. You can see these all materials have been tried uh, by people. This is anti-fouling applications where we are developing these kind of thick layers, even multiple layers, right? So we have the substrate, we have alumina, we have copper, and so on. So these metallic glass coatings are also being explored. Well, in the coating area, we can have other potential areas where those who want to work, they should explore these all equipment, these new applications, because the cold spray needs to be looked at for several other applications. It's up to you how you guys can think over and explore its application. There's a wide amount of scope in cold spray area where you can do some novel work and get good publications and maybe commercialization also and so on. Then let me spend some more time on. Of course, by now you get some advantage, kind of understanding that how cold spray can be good option for additive manufacturing. But this is more like systematically, I want to put it here. One thing is clear that cold spray can be used as an additive manufacturing, but then how it is standing against the other processes like your laser sintering, powder cladding, wire tunneling, E-beam, and so on. So cold spray is here actually. Okay, this cold gas dynamic modeling or manufacturing, and this is also cold spray, right? So we are in general cold spray can be put here actually. Okay. Now what this graph shows, the cold spray can give you very good deposition rates, but in case of shaping fidelity, we are low actually. There what does mean? It means that for very complex shapes, cold spray has a limitation. See, after all, what we are doing, we are exploring this the movement, relative movement between the target and the cold spray, right? So, which is restricted, of course. But in laser sintering or powder cladding or this E-beam, you can produce. By now, you must be seeing some presentation in this program itself that these conventional additive manufacturing processes can develop very, very complex shapes. But cold spray can't do it. So cold spray will be good where the shapes are not very complicated, right? But shapes may be big. So it will have its own niche area, cold spray. But why it is attractive? See here the deposition rates. Deposition rates are very, very high in this case. You can see laser sintering lies here. These lies here, almost double of deposition rates. And this is, one of the major attractions in the production lines, right? Industry wants to have very high deposition rates and so on. So that way, um, this is something. Some lesson from here is that if the shapes are not very complicated, it's good to explore cold spray. But if the shape is very complicated, for example, you have fins and very undercuts and so on, then it's not very good. So, from my experience, what I could say you that cold spray will be good option when we have some symmetrical uh, objects to be manufactured, right? I'll show you some of those. You will understand that. Now, why cold spray? We can low process temperature, absence of thermal stress. This is another one important kind of advantage. Of course, we have understood some other advantages, but this is also one. That since the process temperature is low, we don't have the thermal stress in our part. So you might have understood the defects in the additive manufacturing processed parts, right? By now, that there is the presence of some thermal stresses, right, owing to these high temperature involved in lasers and so on. Severe plastic deformation and low temperature, more refined homogeneous microstructures can be obtained here. As I already showed you that here we get some severe plastic deformation happening, which leads to grain refinement. And once grain refinement is there, you can get very better kind of properties, right? So if you see the fatigue stress, the fatigue strength of cold spray process parts are very good actually. Why? Because we are getting net compressive stress in the deposits. Whereas in your other processes, you will get net residual stress. If I say residual stress will be tensile most of the processes in these most of the processes. But here it will be compressive because you have a severe plastic deformation, which is basically giving net compressive residual stress, which is helpful. Low oxide strength, oxided porosity content, of course, we understood. Depositing temperature sensitive materials, nanocrystalline nanoformers, and those prone to oxidation. All these materials can be deposited by cold spray. What is the limitation then? Limitation is very fine powders cannot be. Let me tell you, you think about cold spray right now only when the particle size is from say 20 to anything between 100 micron or something of that sort. If it is less than 20 micron, it becomes very challenging. Okay. Although we have done it for 10 micron also, maybe that particles were good enough, but I will prefer 20 micron upwards. Temperature sensitive materials, of course, because temperatures are not involved here, you will not get use of your nanocrystallinity and so on. Fabricating material with high thermal conductivity and reflectance. Now, this is another challenge. If you talk about laser sintering or laser melting and E-beam, etc., when the material has very high thermal conductivity, you know that there will be chances, there will be the problem of focusing the heat, right, in the localized area. As soon as the laser will come, the uh, heat will dissipate, right, because thermal conductivity is high. Similarly, in laser-based processes, especially if the material is very reflective, so you will not get the heat transferred, right? So all those challenges are, well established and well taken care of in cold spray, because we don't have that concern of thermal conductivity as well as conductivity. And material, because it has a mass, so it can be propelled, right? And it can be deformed. So thermal conductivity and reflectors has much influence on that. Good bonding and high strength due to work hardening. Of course, you will get very good bonding and high strength due to work hardening, because material is getting severely deformed, right? So you have these stain hardening effects in that. High deposition rate multi-material deposition. Now, this is another very important point here. Since there is a lot of emphasis on having composite materials, right? Now, suppose you have aluminum and silicon carbide, and you want to do it with laser sintering. So, what will happen? Both have the different properties in terms of physical properties, like their melting temperature is different, so their thermal expansion coefficient is different, and so on. So that will create a problem in laser, right? So, but in cold spray, again, temperature is not the problem. You can push those materials with a certain velocity and we can deposit. So, multi-component material deposition is not very big challenge in cold spray. Whereas it is a problem in conventional, especially where we use the heat. Less distorted geometries. Of course, because we are not having these temperatures, so you don't have that warping and other things, which can happen in other processes. Potentially eco-friendly alternative compared to laser waste process involving high energy consumption and so on. Of course, because temperature is not a world, this is something, and we all should be sensitive to our environment. Where I usually say to all my students that whenever you do some research or develop some technology, always think about the eco aspect, right? It's very, very important. It's high time that we don't create any more nuisance to the environment. So we are now coming on to some additive manufacturing applications where the cold spray has been used, right? So I'm showing you some of the very practical applications. This is a freestanding bi-material, hollow-shaped permanent magnet fabricated from this material. This is some composite material and pure iron using cold spray additive. This kind of material components have been manufactured. This is a multi-layered titanium copper object, and it's cut fragmented by this. This is any cross section. So this is a multi-component material. Again, if you do these kind of things by laser, of course you can do it, but then there will be kind of, problem at the interface of titanium and copper, because copper will also react. There can be some kind of chemical interaction or diffusion at this intersection, right? But here, those chances are very, very meager actually. So this is a hollow cylinder with end cap and a bracket produced from cold spray, right? These are all met components which have been made. This is another interesting application. So here we have inner wall of a pressure ring for a food processing machine. This whole thing has been made in inner one, small sized cold spray nozzle. This is an inner wall of small space cylinder tube, right? So this is one. This is an aluminum alloy tube. You can see aluminum flange, copper cubide. This is very, very interesting application. This is a rocket nozzle by Impact Innovation. Impact India also wants to make this this is traditionally made by some other processes, which takes months and months actually, several months. But by cold spray, it has been made in less than 30 days and so on. I was seeing some video. I suggest you to see. This is available in open space domain. You can see that this impact innovation guys, they have made this by cold spray. Um, this is another CSM copper ledge, right? Which is made. One caution I want to do here is that we suppose you these products right now are very high-end products actually. These are not for common use actually. If you say I want to make this flange for my home, centrifugal pump and so on, I will not recommend it because already we have very simple cast thing, right? But maybe in space or explorations or in transportation sector where there is a threat to human lives and so on, where you can't afford to have defects in the parts and so on. There you will be thinking about these kind of investments. This is another, repair. I was telling you the cold additive repair applications. So these are all parts which are aerospace parts or costly parts. This is the front frame or T-cells. Now, during the usage, they will get wear and tear, right? So these all kind of damages will happen, right? And cold spray is a process which can help you. This is before, this is after. This is before, this is after. This is before, this is after. So on. So you can see how these parts have been refurbished with the cold spray. Now, why cold spray? Because by now we understand that the whatever deposit I will make here will be almost having the similar chemistry of the base, right? Whereas if you repair it by say weldings or some other process, the geometry may not, there will be a diffraction in the properties, which is not good actually. Because we will be having different type of deposit. Slightly difference will also cause some kind of problems in terms of say, corrosion, some other fatigue, and so on. Right. So those things can be, avoided. You can see this another part. This whole thing is broken, so they refurbished it and then they machined it, and they have made it like this. So these are restoration process of aluminum alloy blades by CSM, right? So this is a code structure. This is again supplying gear made on the shaft itself, integral, right? So this is another interesting application by cold spray. So a shaft के ऊपर supplying. These are permanent. These are not fixed on it. Rather they are made on it, right? Additively manufactured on this. So this is another application. There are again repair applications. These very costly processes. I have seen some people repairing these gas turbine blades in aerospace and space. These are very costly actually. Each of these blades will cost the repair is only say very cheaper by cold spray and so on, right? And you get the same property almost, and working life can be extended. Another very interesting additive manufacturing application could be joining of similar metals, right? So there are different strategies. So this is a hole is made and then chamfer and then cold spray aluminum fill is done and then it is machined and you get this part, right? There are some other copper embedded coatings for several other parts, right? So where even on the polymer, copper has been attached. It's another joining application where they have done some FSB also, FSW also. In between they deposit this aluminum and then FSB has been done and so on. Maybe some customized application is there and so on. Then This is another very interesting study in 2023 itself. People are saying that, even we were saying that there is a ductility, loss of ductility into the CSM deposits, but somehow this group has developed these 50 mm, see 50 mm thick copper coating on aluminium, right? So it's like a 5 centimeter, right? So when in our manufacturing, once this is more than so sorry, this becomes like a sheet. I mean a thick. This is like a plate, right? 50 mm. So once we are beyond, I think 4 or 5 mm, we call it or 6 mm, we call it a plate, right? In our manufacturing, normal manufacturing. And from those plates, we make so many parts. So that is the line here. So anyway, this is done. These are some of the parameters which we have used. No post-processing has been done, but still they are getting 43% elongation to failure, right? So they go to this kind of what they call bi-model grain structures. So nanocrystalline grains have been seen, okay, which help in relieving the stress induced during the impact in this one. So this could be interesting. I have not read this whole paper, but this should be studied. And they have compared it with some other uh, processes as well. Pure tantalum deposit on CSMM. Again, 6 mm thick tantalum coating on copper has been produced. This one. Okay. Tantalum has it has an application of electronics, biomaterials, cutting tool industry, right? So a lot of applications can be explored in that demand. This is oxide dispersion strengthened coatings via CSM, right? So this is copper aluminum oxide coated on this one, right? So this is a kind of ceramic what we are adding some binder to it, right? So that is to eliminate the uh, problem with this one. Right? So this deposition is happening. So this is alternative to traditional powder metallurgy plus hot extrusion process. As an alternative to this, they have given this heat exchanger devices and equal power generation, etc. So this is a porous T64 coatings, right, with cellular structure. This kind of structure they have produced so that the cell grows in these porous regions for biomedical applications and so on, right? So this is also, I would say, interesting application. This is a highly reflective aluminum coating deposited by CSM. Okay, 1.5 thick coating. So in the solar panels or optical devices, these kind of coatings can be deposited and so on. There's another, hybrid approach. See, this is conventionally made. Some part is made by this one, conventional, right? Selective laser melting, and then which is DAY-6 and on that, for some application, they are looking for some coating on it, or some part of that part is made by this aluminium plus alumina, right? So see how nicely they have done cold spray and SLM. So it's like merging both the processes. Our conventional heater and our this one, right? And then they have done some this very application as a structural material field of aerospace and automotive high strength and reduce total weight and material costs, right? So in fact, this kind of functionally graded approaches have been very successful and have been considered for several applications, right? Now, these technologies like additive manufacturing, both conventional and non-conventional, they give us kind of flexibility in tailoring the materials, है ना, as per our requirements at the required locations. Now this brings definitely a lot of advantages, right? In terms of weight and material cost and so on. This is another repair application. Corrosion damage has happened, but then they have refurbished it. Here they have done this nice study that different repair strategies has been given. Here is a trapezoidal fill up has been done. Here it is conical. See, this is the structure to be repaired, and this is the deposit by cold spray. Here it is this one, trapezoidal. Here it is spherical. Okay, so maybe it is some study where they are looking for better repair strategies and so on. This is some work which we did actually on this coatings. Not coating, these are standalone deposits of nickel chromium alloy. So you can see very thick 10 mm and so on we have produced, and then we have seen their properties in terms of their mechanical properties and so on. In fact, we developed this titanium as well as this nickel chromium deposits, and then we characterize them with regard to their mechanical properties as well as corrosion properties. The correction here was, if I was to tell you, that we could deposit very thick titanium as well as nickel chromium, one aspect of it. Another thing was that the properties of these thick layers were compared with their as cast conventional counterparts. For example, titanium, this titanium deposits properties were compared with the as cast titanium, and you will be surprised that we were having certain better properties in this in terms of mechanical properties, again owing to those severe plastic deformation effects and so on. So for example, modulus was better here and so on. But of course at the loss of ductility, and that's why you have to sometimes go with heat treatment and so on. I'm just summarizing now. Not summarizing, I'm just now trying to finish this talk, complete this. But one aspect which I want to tell you all is, as I indicated earlier also, those who want to work good in, this modeling work and, simulation work, there's a lot of scope actually for those people also. And if you see the publication, people are encouraging, a lot of efforts are being done mainly to understand this process by these simulations. It may be based on molecular dynamics, it may be on your computational and fluid dynamics and so on. Different approaches have been used. So still there is a need to understand bonding mechanisms, nozzle, and other aspects of cold spray. These are helpful, and in my opinion, they will help us to on one side understand the process. On the other side, they will give us the economical use of cold spray also. For example, as I told you in the beginning itself, that it sometimes becomes very difficult whenever I get the new combination of materials to be deposited or to be processed through cold spray. The challenge becomes at what parameters we should start, right? And if I go randomly, means I will be spending a lot of gas to arrive at the optimized parameters, right? So, but now we have some of the models which are very nice to predict those process windows for these unknown materials properties, right? So that is where I would say that there is a lot to be understood through simulations also, and those who are good in this simulation and modeling, etc., they can do their PhDs in this simulation aspects of cold spray also. There's a scope actually. That's what I wanted to say. This is, for example, has been shown very nicely how the adiabatic shear instability is helping us, right? So within a very small time, you can see the stress drops. I was telling you that at the interface, the stress drops. This is what we call shear adiabatic shear instabilities, right? And the temperature rises very highly at that. That's why this goes. And strain rate also. Strain increases all of a sudden. That's why we get this thing. Similarly, yes, this is again when we say use of cold spray for additive manufacturing. Just like in other processes, you might be listening to some other talks, even in the conventional additive manufacturing processes. The challenge is always to have this path planning, right? So same way, cold sprays, if you want to deposit some kind of complex shapes through cold spray, obviously there has to be lot to be done in terms of robot path planning, right? So again, those are who are good in this robot path planning, etc., they can also do very good job, um, for making certain specific geometries economically and so on. Lastly, I think this is my last slide. This is what is the dream. We are talking about Industry 4.0 now. In fact, now people are talking about 5.0 also. So the same, this Industry 4.0, our systems, thermal spraying systems, cold spray systems, they have to be compatible with that Industry 4.0 frameworks. So if from that angle, if I see my cold spray systems, we have the spray modules. So you can have several modules in our cold spray lab or setup. One is a robot module is there. One is the spray module where we have this gun and we are exploring it for gases and other things. And then we have post-processing module where heat treatment was, and inter-process module where milling, blasting, drilling, etc. And we have this in situ measurement. Now, this is a very good kind of, and the challenge is to can we make a closed feedback system for all this. Basically, Industry 4.0 is to how to connect these all so that they work as an autonomous manner, autonomous, not automatic, autonomous manner, and we get the continuously outputs from this build up, how it is built up, and if there is some deviation in those properties, we can kind of control the process parameters and so on, right? Again, there is a lot of work which people have done actually, but still there is challenge because when we are depositing the material, so usually what happens is usually people say spray and pray, right? Means spray kar do, let us see kya aata hai, right? Means we are always afraid of, while spraying any material, we are always afraid that what kind of material properties we are going to achieve. And there is not much know-how to know what is happening in dynamically over there. Means I will have no idea what will be the porosity level while it is being deposited. The only way is that I will deposit it first and then I will characterize it, right? So that means whatever gases and whatever consumable I have used are used. So imagine a situation if I could dynamically see whether in situ measurement, whether it require porosity is coming or not, right? If it is not coming, then I can control these parameters, spray module, right, accordingly. And there could be other properties also, maybe surface roughness, and so there's a lot of scope actually, what we call machine learning AI to be implemented here, that we can on-site, monitor the part to be built up, and if there are some deviations, it could be controlled. Okay, and of course, this whole thing could be connected to cyber or cloud and so on. So these are some of the further kind of developments which we are looking forward and so on. Thank you very much indeed. I hope this makes some sense to you guys, whatever I spoke today. So this is a setup which we have at IIT Ropar. Okay, so this is the robot here. This is the gun basically. This is bottle feeder. Other things are controls, and this is a caustic chamber and so on. So thank you very much indeed. And if there are some questions, we can always discuss.
Thank you, sir. Any questions from the online participants?
Sir, one question, please. Sir,
Yes.
if the pressure we are changing like 10 bar, 20 bar, 30 bar, 40 bar, so is there any simulation we can do that in between this 20, 30 and 30 and 40, that what is the trend in change in the deposition we can study by this?
Yes, we should actually. There's a need, and there are some models on this also, of course.
Sir, may I know some a few tools which we can do this parameters while changing the parameters, we can see the trend.
Yeah, in fact, I'm not an expert in that, but you write an email to me. My student Binay is very good in that. I'll connect you with him, no problem. So
Okay.
we are using right now Abacus and the CFT simulations. So those can help us.
Okay, sir.
But there are some special simulation softwares also for that purpose. Two of my students are doing good job in that. One is Parminder Singh. He is now applied materials, so he'll come back. I can connect you to him also, or Vinay Gitla. Not a problem. This is not a big deal. Just write an email to me. I'll connect them.
Okay, sir. Thank you so much.
Yes, Rajkumar. Do you have any query?
Sir, good morning, sir.
Good morning.
Actually, it is a very informative session, sir. So, my area of interest, as I belong to an aerospace engineering department, so the area of interest is about what you said about thermal barrier coating. Usually, I think that thermal barrier coating will be done on a plasma clay method, sir. Yes, sir. Actually, how it will be applicable for a cold spray method also, sir?
See, cold spray has a when you talk about TVC. So TVC upper layer, we can't do anything with cold spray, right? Which you have this typically zirconia and
ceramic coating, and will be having a
ceramic, right? But there is a bond coat, as I told you earlier. Bond coat, there is some sort of research which is going on. That whether we can develop these bond coats by cold spray or not, because traditionally they are being used by conventionally by plasma spray itself, as you said. But there is some issues in TZO formation and so on. So this two aspects people are exploring by cold spray. One is to explore these nicroly and this chromium nicroly type of things. Sorry, cobalt base, this cobalt, chromium, aluminium, yttrium kind of bond coats through cold spray. Another thing they are trying is to use to replace this nicroly systems by HEAs and so on. So our group has not worked on that, but I have seen some literature where cold spray is being explored mainly for the improvement of this bond coat properties or bond coat quality, not the upper layer, right? So that is where.
Okay, sir. Actually, when we have a bond coat on a top coat, there will be a delamination at a higher temperature. Yes,
Yes.
sir. To overcome that, we can able to adapt FGM coating. Can you able to have that FGM coating into the cold spray method, sir?
See, FGM coating will be only possible if all materials are being sprayable by cold spray. But in bonds, if I understood your question, you are talking about TBC system, right? In
Yes, sir.
TBC system, the upper layer has to be ceramic, right?
Yes.
And ceramic cannot be deposited by cold spray. That becomes the obstacle. So choice of cold spray for TB system is only limited to the bond coat. Now,
Okay.
why people are trying to use for bond coat? Because that TGO which develops at the interface of this bond coat and your top coat, that is the ceramic, that TGO is growing at somewhat higher rates, the currently plasma sprayed one, and which leads to delamination, right? So this TGO growth has been reduced through cold spray process. At least there are some experimental studies or scientific studies on that, which you can find from the literature. So overall, अगर आप कहोगे, it's difficult to use that FGM approach for all the layers, right? So that's why if you see one of the studies, probably one material was developed by SLM and then the other is sprayed by cold spray. Probably in there also their approach would be that the lower portion would have not been possible by cold spray. So what they did, the lower they produced by SLM and then the upper coat they developed by cold spray. So those kind of multiple or hybrid approaches have to be adopted. And TGO is not, sorry, TBC is a very complicated system. To my knowledge, cold spray can be helpful only for bond coat. Not much scope is there.
Okay, sir. Thank you, sir. Actually, what ma'am asked, I also need about the simulation tools, sir. Probably,
Simulation.
yeah.
Yeah, simulation tools, I can connect you with my students, not a problem. We are doing a lot of simulations. But all are done by this convention only. Abacus is big help. And they are using some CFD and so.
Okay, sir. Thank you.
Okay, anybody else from the online participants or offline participants? Anybody has any query? You may ask. Okay. Okay, then we'll end.
Okay, thank you, Anuj, and thank you all the participants. Please don't hesitate to write to me. Actually, my email is straightforward: harpreetsingh@iit. And as Anuj told that this is a national facility, we want to help the students to the extent possible. Because in doing that, we will also learn about new things, right? So please don't hesitate to write me an email, and we will definitely help you to the extent possible. In fact, the major obstacle in my eagerness to help is the consumption of nitrogen in this system. So whenever a student would come, I would ask for a lot of money for nitrogen. But now I have got Center of Excellence in this coatings, and we have got some grant where we have got good money to set up the nitrogen plant in-house. Now this will help us to reduce these coating charges to a tremendous amount. So we'll reduce it, but that will, in typical government system, it takes 6-7 months to purchase and install those things. So once that a nitrogen is there in house, then only it will be your powder which you have to bring and some charges based on hourly based of this system. Then I will be able to help you guys more. But my willingness is always that it's a national facility and we should take advantage of this and do some good research. Yeah. Thank you very much for all of you to listen to me and giving me this opportunity to interact.
Thank you, sir. Thank you very much for accepting our invitation to give this beautiful talk. And we always inspire from you. in regard to these voting purposes, and will always try to come to you much more as much as we can for the voting purposes. And thank you for considering, you can say, building a nitrogen, you can say, in-house plant, maybe in the next 6 to 7 months. Thank you, sir. Thank you very much.
Thank you. Thank you very much, and all the best to all of you guys. Thank you very much. Thank you.